All right, good morning. So today we will walk through the mechanisms of deepfake generations. There has been massive improvements or massive amount of advancements in the last couple of years. So we'll not be able to cover everything, but we'll be able to touch upon the key works in the domain. And then towards the end of the lecture, what we will do is we will generate our own deepfake. And for that, I have uploaded the code on the day 3. There you can see some one Python file and a couple of models and then some sample images, right? So that's what we're going to do. And then completely towards the end, what we're going to do is that we're going to use those generated synthetic images or deepfakes and then try to evaluate with the face recognition system that we learned on day number 1, right? On the day number 1, we use this arc face models, cost models. So we'll just try to see how they actually can impact the face recognition system. Sounds okay? Okay, all right. So let's start with understanding what is a deepfake. So most of you might know that deepfake is typically this kind of uh, an image that is generated by using the deep learning and then trying to create like a photorealistic content, which could be audio, video, image, or multimedia, right? Um, Typically, a deepfake is what we create for, let's say, for recreational purposes. But what has happened in the recent years is that that has been used for multiple illicit use, right? So this is a problem which we are trying to solve. As long as it's for non-harmful use, I think it's okay. People can laugh at a video and then they're fine and then they move on, right? But as long as it is impacting the security, that's when we start getting concerned. So here is a video. I don't know if you can identify this person on the left side. So you have the video, and then you have on the right side you have the generated video, which is completely seamless, and you can see that it has been manipulated. And if I did not show you the image on the left side, you would not be able to detect if it was deepfake or not on the right side. Make sense? So from the day one, from the time it was actually being the first time it came out to what we are seeing today, we have seen the improvement of quality in terms of leaps and bounds. Okay? So we will try to understand what is behind this technology, and then we will try to see how we can generate our own deepfake. All right. So how did people start looking at this deepfake? So if you looked at the history of deepfakes, there was this one post on Reddit which called as I mean, if you follow Reddit, anybody follows Reddit? Some of you, yeah. So it's like a forum, right, where people can go and discuss, and then people can ask questions, and then they post something funny, post something more informative, and so on. And on that platform came up a thread which is called as deepfakes. That was more or less the first occurrence of when people started to know about deepfake. So what they did was that they introduced this deepfake in an attempt to synthetically replace some celebrity for adult video. Right? So that's when people started getting a bit more concerned about this technology. Now, right after that, at that point of time, there was still a possibility of thinking that the technology is very advanced. So we sitting in the classroom will not be able to recreate this one. But then things changed very drastically, and things changed drastically in the sense that they were not only used for such. The first occurrence came for this kind of adult video, but right after that, people realized that it also has a potential for very positive applications. So in one of the positive applications here, it was this famous football player who was talking about ending malaria across different countries in different languages. So the idea here is that you have only one video and then the audio is being injected, which is completely synthetic, right? So the person doesn't really speak the language, but then you can generate such kind of videos. So you see that there is also a positive side of that. And then also in the other side, you also have a very brilliant use case of this one in the the media industry. So you do not really have to film the entire content. So what you can do is you can film something, a chunk of the video, and then you can completely recreate the video for a different person, different appearance, different background, and so on. So here on the right side, you see that there are some applications up there where you can inject the video into the or audio into the video stream and then completely replace it. And on the right side, you also see that the facial appearance of the person has been changed. So if you want to create a video of somebody who's quite old and then want to project them as younger age, you do not really need to find this duplicates, stunts, whatever you call them in the media industry, right? Typically, that's what happens. So in this case, you can very easily manipulate, and then you can put the frames back into the video. So these are some of the applications, but then you also have this kind of a bit of concerning applications, such as you can have the celebrity industries for adult movie industry, which is quite bad, right? If I'm going to create such kind of images, then neither do I have the permission nor I have the authority to do that, right? So, which I'm kind of misuse of the media that is publicly available. So now we are talking about all the media that is publicly available on social media. So all I need is to get access to your image on your social media, then I could misuse it for whatever that. And then the other aspect is also this election propaganda. I don't know how many of you actually have followed this. You could take the video of a particular person, let's say a leader in a political party, and then you could make him speak about things that he doesn't really want to speak about, right? And this could be used by, let's say, activists. Let's say we can use it for opposition in the political parties and so on, right? So this kind of creates a concern, and there is also this other aspect that I was recently told. Right before the election, there is a gag order, right? The leaders cannot go out and make a speech. But what can be done in this case is that you release a video just the day before. Right? And me as a malicious actor, what I could do is I could create a completely different plan for the elections that makes sure that the votes are flipped and the disinformation is spread. Okay, so this like the corner edge cases of the deep fake. So uh, which is not completely in the media industry, but more on the societal impact. So as long as we talk about the societal impact, so we have to be very aware of how we solve this. So solving this part comes on Monday when we are going to reconvene again for detection approaches. But today we will just try to understand the deepfake and then we create our own deepfakes. So let's look at the history of this deepfake. So if you look at this history of the deepfake, approximately in 2014, the renaissance of deep learning came. Now, why do we say it as renaissance of deep learning? Because in the earlier days, it was not that deep learning was not there; it was just not possible. It was just not feasible to be run on a local machine. Right? We didn't have the computation power, so all we had was this CPUs, and on CPUs, even running a simple MLP was very tough. And then 2014 came the breakthrough on the ImageNet, and the ImageNet introduced this architecture, which was very simple and elegant. So you had these two streams, and then from the two streams, you are kind of extracting the information, and then you are classifying the image. For those of you who do not know what ImageNet is a database which is typically having thousands of classes, and then with multiple samples per class, and then you are classifying. Right? So that's the idea of this. And the accuracy on that ImageNet in the classical machine learning was quite low. And then in 2014, the approach that they proposed came up to be so good that it bet all of the existing methods. And then suddenly deep learning was on the rise of increase, on the verge of increase. Okay, and then what happened after that? Now, most of you might be thinking that the generative AI that we are talking today is something very, very new, but this actually not very new, right? So if you look at this architecture here that is shown on the right side, you see that the architecture came out in 2014. And in 2014, all they did was they took these two generative networks. So what this called it as generator, and the second one they called it as discriminator. And the idea was to introduce a two-party player game. Okay? So what the generator is trying to do, generator is trying to create a fake sample, and then the fake sample is created, and then it looks at the real sample and then tries to see how much different they are. If it's not different, you send it back in. Right? Now, the interesting thing here is that here what we call as the latent space could be, oh, right. So the latent space that we see here all these color coded symbols. This could be something very, very trivial, as in a bunch of feature vectors, bunch of numbers that I have, or it could be something that I've learned meaningfully from some other end, right? So just to give you an example, let's assume the face recognition system that we have. From the face recognition system on the day one, we extracted the embeddings, which were of dimension 512. Now, if I have this 512 dimension, can I recreate them? So I can easily add some noise to that and then generate a sample from this. And once the face image is generated, I have my real image. Then I can see how much it differs from the real image. And then I can tell it, okay, you know what? I did not like the image. Go back and then update the image. Right? So it's as simple as that. So now, now at this point of time, you can already imagine that if I make this one better, the whole pipeline becomes better, right? If my latent space is very good, if I can represent every single thing in that latent space, then I can generate the samples that are very okay. So this is the whole idea of this generative adversarial network, and this came in 2014. Um, at that time, the results were not very impressive, but I'll show you some of the results later on. And then what it led to is like around the same year, approximately 2014-15, there came this project from DARPA. DARPA is this defense agency in US. They kind of already realized that there is a problem here, right? So people could use it for creating whatever the fake content and compromise the security. So there is this first project that came out as media for, and the idea there was to just look at, okay, what is the possibility of these images? What can we do about them? And is there any hope for us for detecting? So that was the idea, right? And then came a paper which was a breakthrough paper in 2016, which they called it as face to face. And now the situation became slightly relaxed in the sense that you didn't have to have this advanced knowledge about the whole deepfake. All you needed to do is that you have a target, you have a source, and they could capture the image from. In that case, they used a RGBD camera, which is RGB, the regular images, plus the depth. Now, by using the depth image and the RGB image, what they could do is they could transfer the expression to somebody else. So here, there is a person. This is the actor, and this is the source person. Now, the source person is saying whatever he or she wants to say, and that is easily and seamlessly translated to the video of the target. Now, this kind of gives you unlimited capability, right? So you could take any video and then you can put in any kind of content. Okay? So 2016 was a paradigm shift in that sense, and then came now if you remember the GAN that I introduced in 2014, that was introduced in 2014, the second part. Then came in 2017 a major breakthrough in architecture, which we call it as cycle GAN. Now cycle GAN is again based on the same idea of GAN, just that this is the typical scenario where you have this uh, one generator and one discriminator. Now, what is happening in this case is that you have this two images. One is that you are having a real image in domain A, and then you have a fake image in the domain B, which is generated from this. Now, the generation, if you can pay a very close look at this, you see that this is zebras, right? And this is some kind of horse, right? And now, where is what we want to do is that we want to create zebras to horse by transferring not just the content, but also to transfer the style, right? So CycleGAN enabled this by making sure that there are two different generator architectures, which is A to B and then B to A. So when I do A to B and B to A, so if my generator, if this whole pipeline is good, I should be able to recreate this image to this image, right? So all I'm saying is that convert water to I don't know, coffee, and then coffee back to water, like in terms of the analogy. And as long as I have that mechanism of converting this image back to this image, then it means that I can trust this network and I can also trust this. Okay. So for the sake of simplicity, just assume it as a model, any model, right? And now this model, whatever the output is generated, then you have the real image. Now I can match this one with the actual image that I have, and I can say that, okay, now I am in a position where I can generate any kind of fake images. So CycleGAN in 2017 was another major breakthrough work. And then came this work in 2018, approximately in the end of towards the end of 2017, which really demonstrated it on a large scale, well, in a small data set, but that what kind of capability was available. Okay? So now they took some kind of video from the White House proceedings, and then they just converted and edited it so much that it was very difficult for people to identify if it was real or fake. And the paper was called as Synthesizing Obama, in which case the whole sequence of the lip movement was. Now, up until here, the previous case, people were only considering the images, right? So that means if I had two images, then it's easy to deal with them. But the moment I have videos, what happens is that the moment the way I speak, there should be a continuity between the points. And that was still an unsolved problem. And that problem was solved in 2018. The paper came out in 2018. And exactly at this point of time, you can see that until this point of time, everybody were thinking it's a complicated technology, very difficult to run. And then came in 2018, approximately in February, I think in February 2nd, where they showed you do not really need such kind of expertise. So you could just download the code from there, and all you needed was to run it on a terminal. Right? So suddenly everybody could create these deepfakes, and from then on, I think when I took it, it was around the 2.9K downloads, but I think now it's even more. But then there is this other one which is already having this approximately 40,000 users who are using such kind of code base. Okay, now if you go back to GitHub and then try to look for deepfake, you will find even more number of repositories, both in terms of technological capabilities, in terms of approaches they are using. They might be using GAN, they might be using diffusion, and so on. Right. So the idea here is that everything that we have been doing so far is very easy to achieve. And then came this other work in 2018. So all the works that we have been talking about here is like small data sets, right? Like very limited number of samples. And then came in 2018, approximately in March, there was this first data set that was released, which is called as, it was released by Technical University of Munich. The data set was called Face Forensics. And then that suddenly showed us it was possible to create millions of images. Right? So there are two things about this. So the moment we are able to create these millions of images, I can use them for creating better deepfake generation. On the other side, I could also use them for training models to detect them, right? So you have both the advantages. So then the field kind of exploded since then. And now yesterday night I was trying to look at what is happening recently. And in the recent years, you can see that from 29 onwards, before 29, you can see all the methods that were proposed was on generative adversarial networks or variational autoencoders. I think you remember it from the day one lecture of Professor Oja. And then in 2019, approximately, the first paper on the diffusion came out here in ICML in 2015. And from then on, the explosion happened with all the deepfake creation. So this is some of the milestone works. But if you look further down, I'll show in the last slide, one of the last slides, how many works are currently available in deepfake. All right, so this kind of should give you an idea that if you are starting to work on any deepfake generation or detection approaches, you need to at least consider this milestone works. Okay? And then you will always have a number of different works. There is a special mention of this StyleGAN and StyleGAN 2. You see that the two that is coming out in 2019 and 2022. So there is a specific importance of them in the deepfake. I'll talk about that in a short while. But if you just look at them, now if you go back and then try to understand what is happening in each of these uh, good works or each of these milestone works, the idea here is that you have this latent space. It could be any noise, and then you're able to generate the, right? So the very first generation that they created these deepfakes, you see that the image quality is not that great, but still they showed that it's possible. Right? So all the images that you see on the right side here, which are highlighted in the in the yellow region, they are the images that were created. In fact, all the images are created from them, but they showed that at certain point of time, you get very high quality images, right? So comparative. Now you should not think that this is very high quality image for today's standards, but you should think about it in 2014, right? So 10 years almost. Okay. So the idea again is remember everything that we have been doing in the deep learning is exactly the same here, right? You have this generation mechanism, and then if you don't like, you send it back, and then once you send it back, you are fine tuning the model, right? You are updating the weight so that it becomes better and better. Okay, and then the other point of this face-to-face was not just the expression transfer, which I showed in the first slide, but now it could also transfer a lot of other things. For instance, if you see the online RGB video, it takes RGB, the white light information, plus the depth information. So this also means that it's also able to capture the identity of the person, right? So what we want is that we want to remove the identity, right? If I'm trying to transfer my face image to one of your face image, so what I want is that I do not want my face appearance that is here to be on this one, except that I want all the other aspects, pose, expression, and illumination, and all the other aspects that you want, right? So in this case, they kind of showed that it's possible to disassociate associate the identity and then only transfer those three aspects. Okay? And then once you have created that, all you're going to do is that you transfer the expression and then you retrieve the mouth and then you composite. Composite is nothing but merging the two, right? Okay, so this is what they showed, and then again in the next part, so there was this the extension of that work came in also with the from the similar group from the same group in fact. And what they showed is that it's possible to do a synthesis of facial image, both in terms of facial structure and also the reflectance of skin. Now, why does reflectance of skin become important? If I know that the person is standing in a white light, where the light is falling on the skin, then if I'm creating a fake video which does not have that similar kind of appearance, then anybody can easily spot it, right? So you want to make sure that the reflectance is also transparent. And then in the second part, they also showed that they formulated it as a energy transfer, in the sense the energy from one place to other place gets transferred without loss, and that was the formulation. And then they introduced three different aspects. One is the consistency of the photo, how consistent is it, and the features should be aligned, right? So these are like inherent demand of the system. And then they also introduced something called a statistical regularization. Along with that, they had expression transfer, and then they had this mouth retrieval where they were learning the similarity and frame to cluster matching. And then what we mean by frame to cluster matching is that if you're creating one frame, it should be in the neighborhood of those other frames. Right? So one frame cannot be of a person, let's say, completely being quiet, and the other frame being the talking frames. Right? So it should be in the close vicinity. Okay, but then although they did so nice work, a couple of limitations were still remaining, and one of the remaining steps were that the number of steps were rigid. So they had to follow this A, B, C, D, E to get the output. So if you missed one of them, the output would not be good. And then the other thing is that it assumed it has a Lambertian reflectance. Uh, I'm not sure how many of you know about this reflectances, but if you look at the theory of reflectances, there is this. If I have a, let's assume for the sake of simplicity, if you assume a spear, a metal spear, then the amount of reflection from each point is very different, right? Compared to something that's very flat, right? Which is the similar thing in the face as well. So we have the structures, we have the how do you say, we have this depth in the eyebrow regions, and then the cheek region is a bit bulged, and the reflection will also vary. So in the first model, they had this assumption which is based on Lambertian model, and that would mean that the whole of the face would be uniformly reflected in mono. Yes. Right? In a sense that you see that all the images are very bright, right? While you look, if you look at this person, person transferring this image, you see that the shadow is there on one side. Okay, so that was one of the limitation, and then the other minor limitation in this work was that it was offline reenact. So which means I have to wait for you to create a video and then take the video with me, go home, and then recreate the whole video and then come back and upload. Which is okay if you're doing for entertainment purposes, but if you're really trying to do a real-time enactment, then it's not the best. Now there has been improvement, but at that point of time, at that work had that limitation. And then the other work that I spoke about as a milestone work, which was published in 2017, here the idea was that you are going away from the frame-to-frame reenactment, but you're also introducing audio into this. Now, if you look at that top layer there, you see that there is an input audio. It could be any sound, any speech of any political leader, and then you are putting that into the lips, right? So now once you're putting into the lips, there comes this idea of recurrent neural network. The idea of using recurrent neural network is mainly because it's a time signal, right? It's a continuous signal. And using that, uh, if you remember from the face detection approaches that we spoke about, there is always this landmarks in the face, right? It could be 128, it could be 64, it could be 512, depending on the configuration that you're using. So if I can isolate the area of the lip and then inject the audio into that, then I can use some kind of graph analysis and then show how the lip should be. So every phonetic, everything that we speak has a certain way of opening and closing of the lip. So you are introducing that. Once you introduce that, what you are doing is that you also need to retime it, because if there is a blank sound here, this mouth cannot be open, right? So you have to retime it, and then once it is retimed, you're combining and stitching everything together, and then suddenly you have everything, right? So now the idea here is that why I'm talking about this is the combination of multiple techniques here. You see the RNN is being used for dealing with the time signals, and then there is a classical approach of putting the video back and manipulating the lip area, and then putting back into the target video, and then there is a stitching. So it's a combination of both classical machine learning and the deep learning approaches. Okay, so now going further from this, what happened in the next work? Here there were some, as you can see already here, right? You can notice some kind of limitations. It has not solved everything. So what was the limitation in this case? You have to really, really take care of the mask region. If the mask region is not very good, then your composition would not be very good. As an example, if you have a mouth texture somewhere here, and then if you're trying to put that one, you see that the way the target frame is stitched is not very good, right? Which makes it easy for detection. Now, the goal of this deepfake creation is to make sure that you have very good quality image, not the ones with the obvious artifact. And then there is also some amount of classical image processing which is happening, identifying where the tie region is, and then you have to put it back and so on. So which means you cannot just click on a button and wait for the video to be generated. So there is some amount of manual intervention to make sure that everything is good. Okay, so further going from this, uh, came this other work, which is one of the works that we're going to recreate today. And this is called as face swap. And the idea here is that you have two people, and then you are trying to take the features of one face and putting it to the other face, right? So here if you look at these images, then you have the face image of this person, and this face image of that person also has the landmarks. These were the landmarks that I was talking about, approximately 68, and you can also make it more dense. You can make it 128, you can make it 512, and so on. So the more landmarks you detect, then you know that how the face is tilted, right? So that is simply like what we did in the fingerprint yesterday. So we said, okay, what is the angle? And then you realign, right? So it is realigned. So it is made straight because I don't care about the rest of the information in the background. All I'm caring is about the face. So I kind of tilt only the face. And then I do the same thing for the target subject. And in this case, the target subject is one of this famous actor in the thing in movie industry. And then what we are doing is that we identify the area where I need to mask it, and then I transfer the face from one to the other one. So here is the final output, which is coming here. And now this face is getting transferred into this image, and then the output is here. And you could also do it the other way, right? All I need to do is that I could invert the persons. I could say, okay, this person goes there, and that person comes here, and then you have a new output for the face swap. Um, Here, what is also interesting is that you have this introduction of this small network in the middle, which does all these operations. It does take the input, does the alignment, and once the alignment is done, it creates the sample, and then it puts back into the original image. Now look at the angle of this original image, right? So I had this angle which was in this direction, and now the face is here also in this direction. It's not straight anymore, right? So the goal is to transfer the face of one person into the other person. Right? Uh, Now, if you do not really pay very close attention to the entire image, you see that the identity of that person is it can be very misleading, right? You can suddenly assume that okay, it's the same person. Only when you take a closer look, you see that okay, this person's face is not exactly the same, right? Which can be an easy way to fool many of the systems or many of the human observers. Okay, so what is nice in this one? So today, when you are running this the exercise later on, you will see how it actually happens. Sometimes the quality is not that great, but then you have to improve, insert a better model. But the whole idea here is that they take it in a very big image, whatever the image size is, 128 times 128, and then they subsample it to make it half the size. So when you do the half the size information, what you're doing is that you're kind of only picking the prominent information. So you're kind of skipping the alternative rows and alternative pixels. So it becomes smaller. And then again, you do it one more level, and all the way you go to the 8 by 8 size. And then every time you're taking the block, you're trying to add it back to the original image, right? So the information that you're compromising, and then if you upscale it, you can put it back. Make sense? Okay. And then by simply doing that, you can you can edit it at every single level, right? So what I'm doing is that every time I'm swapping it, so the information should be consistent. And by enforcing it in the multiple levels, multiple scales, I can generate an image which is quite nice. Yeah? So this is one of the approaches which is again based on the scale space editing in scale space processing in the image processing. Okay, you don't necessarily have to worry about all those convolution and maps and so on, but what is important here is to identify a couple of key points. One of the points that we have to see here is that you have to take care of. Remember, I told about the lighting problems, the first generation. So now we have to solve that, right? And the second thing is that we have to make sure that the content is reproduced, right? So how do I make sure all of them? So I can say I will dedicatedly design one loss function for each of these components. So one component will take care of the content itself. One component will focus on the lighting. The other will focus on the total variation. The other one will focus on the style. So because now what I'm doing is that I'm delegating the tasks through multiple people so that one person is only responsible for checking the lighting. One person is only responsible for checking the content part. And then if I can put everything together, everybody has to be happy to make sure that the face has been swapped in a proper manner. Okay. So now, just for the time being, forget about all the mathematical notation. The whole idea here is that you should remember that there is an image which you have, and there is an image that you want to create, and then you are trying to measure what is the distance between those two images. Now, this distance can be anything, right? It could be Euclidean distance, cosine distance, whatever you would want to. But then there are certain properties for which these laws have been set. Okay, so this kind of helped in achieving better results than the previous one when it comes to the face swap, and this led to the second work or similar work here. Now you could see the results, how drastically they improved from the previous generation of deepfakes. So you see, you have a face image of a famous actress, and then from that famous actress, what you're trying to do is you are inserting uh, another person here, and then you have the third row, which is again refined version of that. So you kind of can have very fine-grained editing of this face image. So when you will work on the sample example today, you will see that it's not as great as this one because the model that we have chosen, which is a lightweight model, is not the best. But you can fine tune it later. Okay, so the other aspect. So I also mentioned about this. If you have the face which has to be in a very ideal condition, then you can get very good images, right? By introducing all these different components, what they also showed is that it's also possible to do the face swap in a non-ideal condition. So what do I mean by non-ideal condition? You see the person is really not seeing into the camera here. Still, I'm able to swap it. Okay? Now there are some obvious artifacts which we will discuss on Monday, but you can still see that the whole pipeline is now becoming better and better for swapping the faces. Okay, and then came a better version of that in 20. Then came a better version of that in 2018, and in this better version, you could see that it's not only the changes in terms of the small variations that we see, but we see very drastic changes in terms of shape and poses. Right? So the idea here is that you are extracting the 3D information using the shape, pose, and then also use the expression, and then you can transfer each of them independently. Right? So you see that in the first part how the different pipeline works, and then there you see one interesting thing is that it's also taking into account the areas that are actually needed. It's not randomly putting everything into the face, but it's looking at how much of the face area is actually visible and then how it can be transferred. Okay, so and then again, the authors were also very creative in showing that it scales up for different applications. For instance, here you see that the entire pose is changed, and then the image is actually taken in a wild scenario, the wild setting. So I think it's always the same person who is being depicted there. I don't know if you remember or identify that person. Okay, so now I'll come back to this one in a short while. There is a implication on the security, but then let's take a look at the gun-based approaches, right? For the for the creation of this deepfake. Now, if you take any traditional architecture, what they did is they take the image and they take some latent space, which is nothing but the representations, and then they normalize it, and then they pass it through some other set of operations, such as the pixel norm, convolution, again pixel norm, and so on. Each of them have their own properties. If you read the paper, you will be able to understand it a bit more. But here, the main idea is to understand that the traditional architecture, whatever was there, they took it out, and then they introduced what is called as StyleGAN in 2018. Okay? Uh, what is interesting here is that it's not a very drastic change in terms of the architecture. What is happening here is that you have the latent space, which is taken from here, and remember the normalized remains. Oh, okay. So what is interesting here is that you see that the normal component is still the same. The first block remains the same as it is. And instead of having this one fully connected layer, they introduced multiple fully connected layers there. And then they introduced a new space, which is W. And this W is what is being manipulated. And the W is nothing but another set of features, right? So it's one features to another features that you're mapping. And from that, they made some changes which kind of enforce that, okay, every time I have some information coming from one network, and then I add some noise to that, and the noise can be anything, right? It could be trivial information that we are putting in. And by introducing such nice architecture, they said, okay, we are now able to generate the images of high quality. Remember, up until the previous architecture, we were talking about the images which were very small, like 128 by 128, 256 by 256. And suddenly, with this architecture, they showed it can also be scaled up for generating high quality images, 1024 by 102, right? So the goal here is that um, one, to generate the images using the architecture, and the second is to make it more uh, in the wild scenario, in the wild setting. So you don't have to have the constraints of everything being being practiced in terms of recipes. Okay. So now, if you look at the architecture here, although I said it's a very nice architecture, now if you see here, there is a small component, this W, right? This one. So if I'm not able to make it nicer, if the W is not good enough, then I'm going to fail in this approach, right? Which is again a limitation which came out here, and they said, well, if I have the idea of not good latent space, then my images are not better. And the authors were also very nice. They were very smart in the sense that they introduced another thing which is called as the truncation trick. And the truncation trick for you is very simple here. If you see at the results that you're getting, if you're putting, there is in the formula in the paper, you see there is a way where you cut it off. And they said anything that is crossing this 0.7 will give you good results, right? So if you end up creating a network and then if you're not able to generate good quality images, then that could be one of the areas where you have to deal. So now, so the style GAN was shown for two different applications, right? One is to generate the images itself, and the second one is to transfer the style between two different images. So here is a good matrix which is taken from the paper. You have the source A and source B. Now what you're trying to do is that you're trying to kind of merge these two to a different person. So you can either just transfer the style or you can transfer the content. So suddenly it's both the things are possible, right? So which means my quality of generation from quality of images generated will be very high. So which is what you're seeing in the bottom line here. So if you take this particular source, you take the source A and then put it onto source B, and then you see all the images that are generated at this point. Okay, so before I go to the next part, any questions so far? So it's a very vast content. I know it's too much of content, but I just want you to give an idea before we start practicing, before we start looking into the code. Okay. Okay. Good. No questions so far. Yeah. If we decrease the layer in the blocks. Okay. So the whole idea is that here, whenever you are trying to get this latent space, right? So here at this latent space, you would want good representation. Now to do that, it's your own network. So how you want to create it with large number of blocks or small number of blocks is up to you. So the more number of the deeper doesn't necessarily mean an improvement in performance, right? Sometimes a deeper network might be actually reducing the information cut. I do not have a straight away answer, but what I could say is that it depends on the application, right? So the number of layers and the number of blocks that you're talking about, right? So it could be depending on the application itself. Yeah? So, but the idea is that you need to have a good representation of that latent space. Yeah. So as long as you have that, rest of the things will work. Okay. Praveen, are you saying something? Then we can't hear you, Praveen. Yeah, maybe you can write this question. Yeah. Okay, so now if I've convinced you that StyleGAN was a very good approach, it created very nice quality images, and if you start paying attention to the generated images, you start seeing something very subtle, and this is present in all the images that are available. For instance, here, if you look at the image of this lady, and then you see that there is a very small spot here, right? You see a very subtle spot, which is very dark. And this was kind of a signature that was introduced by the architecture in all the images that it generated. So, which means if I ask you to tell me, okay, if the image is real or the fake, if it's generated image, then you could simply spot that one and say, okay, this is a generated image, right? Which is an obvious artifact. And this was irrespective of what kind of images that you had, right? And then you also have this two other aspects. It was not capturing all the aspects because of the focus on information, fresh air distance, and the precision and recall curve. So it was only optimizing in terms of accuracy and the appearance. Okay, so we had to solve this problem, right? So then what they did is the authors came up with the second paper, which where they introduced something called as perceptual path length. Uh, what it does is that it correlates the consistency and stability of the shapes. And here, the interesting thing is that if you recall the architecture of StyleGAN 1, it's very similar to that, except some blocks have been moved up and down. Now I'll show you what exact blocks have been moved up and down. Look at this particular aspect. So what they did is they kind of eliminated the area that was here, the B1. They removed that. And what they did is that they introduced the B2 after the standard deviation and the mean was computed. Okay. And everything else remains the same, right? So now we are not taking the average. You're only accounting for the standard deviation, how much it is deviating from the regular samples, and then you're putting it back into the next block, so the style remains consistent and the content also becomes better. So this is again another major breakthrough in the architecture in the deep learning for computer vision, and there you see that it is much better. And this one led to another work which is called as FSGAN. FSGAN is quite nice in the sense it is not dependent on the subject at all. Right? Now it can be applied for anything and anyone, and this also doesn't need explicit training. So far everything that we have been looking at is all it needs a training, right? Once you train the model, only then you can use it for generation. But now at this point of time, the FSGAN doesn't really need a training, at least explicit training. So what it can do is that it can do this reenactment using this landmarks and just the blending part. So here you have a number of frames that are P1, P2, P3, and then you have the information from that. You have a generation network, the GR, and then you generate a new image, and then you segment out the areas, and then you can just simply transfer it to the second. Okay, so this is the idea of this FSGAN, and in the FSGAN, what they did is they introduced the loss function slightly differently, and now they said I need to have this perceptual quality, and then I need to have the reconstruction quality, and then in addition to that, I also need to make sure that the segmentation is proper and the generation loss is right? So you are combining again everything. So now we have these multiple parties who are responsible for one task each, and then we are putting all of them together, so we have a better image, right? So then what happens is that in the FSGAN, you have the source image, and then you have the target video, and the phase swapping is happening continuously in the central part. And then it's the same can be happening for irrespective of the hairstyle, the facial structure, and so on. As good as this is, again, there are some limitations, right? So what are the limitations here? If you see here, You see the real person is in different angles, 0 degree, 20 degree, 40 degree, and 60 degree. And then as you start doing the processing on that, you start noticing a particular signature here. You see the way it is forming a checkered pixels. So you can see that in the entire image, right? So now this also means that at this point of time, it starts failing, especially for the n equals 3 and 60 degree. You see very prominent artifacts. Okay, so FS-GAN is good for some constraint condition, but in all the constraint condition, it starts failing a bit. Okay, so now do I need to do all kind of this deep learning? Can I not generate a deepfake without even doing any deep learning? So there comes the idea of this first order motion model for image animation. So what they did is they simply used the idea of this classical machine learning, classical computer vision, where they took the source frame and the driving frame, and the idea here is that whatever the frame is representing here, I want to transfer it to this particular frame, right? So or vice versa, it could be the other way as well. So all they're doing here is that they're just dealing with the transformations. Now, what do we mean by transformation? It can be rotation, and then it is scaled, or it is aligned in a different way. So all those classical things that you do, also that we did in fingerprint recognition yesterday, it's exactly the same thing. So those are all put together, and then you have a dense motion. And here is the idea of this orientation field, right? So remember yesterday for the fingerprint, we were trying to establish the orientation field, and it's very similar to that, right? So here we are establishing the histogram of oriented gradients. Here comes the idea of just the generation module. So most of the other components are classical machine learning, classical computer vision, and then there is a small part of generation module which gives you an output here. Now, what is interesting here is that it's okay. It's quite okay for low quality images, right? And you are transferring the motion where you are not necessarily considering all the small details, the minute details. So, which is when I share the slides, if you can zoom into the slide, you see that the face structure is not very visible now, but the motion is transferred. Okay. All right. Okay. And then if you look at the images that are generated in a constraint condition, now, without any extensive training, extensive approaches, you can bring any of these face images which are static to motion. You can make them alive, right? So there is a very famous picture of this Mona Lisa in the last but second column, and then even that one is me, right? So which means suddenly to generate, make the photos come alive, right? Which is again a synthetic deep fake. Okay. So this is another code which was released in 2020. I think the paper was also published in the same year. And here the approach is much more elegant in sense that you have the source pair and then you have the destination pair with the mask image and the mask. And then what you're learning is that you're learning an encoder, and then from the encoder you have an intermediate representation, and from the intermediate representation you are trying to predict the source pair, right? So the whole idea is that I give this image, and then if I learn everything properly, then I should be able to recreate the same images without loss, right? So that means what am I doing? I'm learning this module which is trustable. So once I learn that module that is trustable, so what I can do, I can take these two components and put them here, right? So what am I doing? So between those two pairs, I can create A versus B, and then I can also say there is another one which is for B, and from these I have the representations. This is the feature space, and then I take them and then I try to decode them. So by just doing that reconstruction, so I'm able to recreate the face and then transfer the images in a fake manner. Okay, so now what is also good here? So if I learn that entire thing properly, then I don't have to have the source pair at all, right? I can simply put in any kind of information here, and then I can recreate this image package. So now we are talking not about face swap, but recreation of synthetic or creation of synthetic data itself. Make sense? Okay. And this is the code is also available on the GitHub. So when I share the link, you can just download it and run it. Yesterday I tried to run it on my GPU, but sorry CPU. It took a lot of time to run it, so I could not put it for the demo today. So if you get access to a GPU, just download it and it's straightforward to run. So you can just run. Okay, so let's try to summarize something, right? So if you look at the generation pipeline, so you have this typically five different kind of basic neural architectures, which is not entirely true. Now you have the sixth kind, which is diffusion based. So I did not want to introduce diffusion here because it becomes more extensive. Um, so the first one is the RNN based architecture, which is continuously looking at the time signal in a time signal manner, usable for the videos. And then you have this encoder decoder architecture, right? So I give an input and then I learn a representation in between, and then from the representation I can recreate the image back. So that is what is called as the encoder decoder architecture. And then you have the GAN architecture, where I have a generator and then I have a discriminator. So the discriminator is trying to make the generator better, right? So this is another one. And then breakthrough architecture again is this cycle GAN, where we had this cyclic dependency, right? You remember the horse to zebra to horse, horse back to zebra. So that is the idea of cycle GAN. And then at this point of time, there is also this architecture which is called as pix to pix, which is based on one of these architectures, modified version of them. So there they have a similar encoder decoder, which is a generator architecture here, and then you have a discriminator architecture here, and then you are trying to recreate the image. Okay? So now in the case of diffusion, so what you are trying to do is that you are trying to add the noise to image at every step, and then you are trying to recreate the image back by eliminating noise. So you diffuse it in one way, and then you undiffuse it in the other, right? So which is again the same idea which you can use for deepfake creation. Um, then there is also the variants of this deepfake creation, right? Sometimes you might not be interested in changing the entire image. Maybe you're only interested in changing the hairstyle, or maybe you're interested in changing the pose of this, or you are interested in changing the expression, right? So now at this point of time, we are in a position where we can control each of these attributes, the attributes of um, pose, expression, gaze, and so on. And then at the same time, you can also say that, okay, you can fine tune the model by picking and choosing different aspects. You can say that, okay, I want a synthesized image where the mouth is open, right? So only the mouth is open, right? And then you can also say that, okay, I want a particular expression, I want a particular style, and so on. So all these kind of fine-grained control, you can get it from the new architectures. Now, if I have um, if I have such an option, now what I can do is that I can put all of these things together, right? So I have the ability to deal with the depth. I can capture the depth information. Now I can also capture the lighting information using the UV map or the depth map. And then if you start putting all of them together, you have a much better pipeline where you can also create such kind of nice images. As you can see here, the person from XS is changed to somebody else, and then you have this artifacts here, right? You see this around the face area. If you come to this stage, all you need to do is to do some primitive image processing up, image processing, right? So you just need to do some filtering, and then you just need to merge the discontinuity in the pixels, and then you have better image. So the bottom line here is that now we are in a stage where we are able to control the deepfake generation in a fine-tuned manner. Of course, there are some other challenges which we'll not be able to discuss today, but at least I'll show you something. Um, so, for instance, you have the entire face synthesis A to B without touching anything in the image, and then attribute manipulation, like converting male to female, converting a bald person into the person with the hair, uh, changing the person without glasses to with glasses, and so on. Right? And then you have the second part, which is identity swap. So there you can see that there is a person A, on the in the bottom part here, there is a person A and the second person B, and then you are transferring this face to this face, right? And then you're still keeping the style and the content of the previous person. Okay? And then you also have the third one, which is the expression swap, where I say that, okay, there is this person A, which is having, let's say, smiling expression, and the person B, which is having a closed mouth, but I can transfer the expression of person A who's smiling to person B. Okay? So these are a bit more fine-grained controls. Okay. That being said, what are the limitations that we can see even today? So one of the limitation is that if you have low quality images, the samples that you're going to synthesize are also going to be very low, right? So that is natural and it's understandable. And then some of the generation mechanisms have this very weird problem where you can see the color of the face is not natural. See that, right? So in the samples that you will run today, you can also notice some of them when you have the non-standard face images. And then if you have a video, there could be some elements that are visible to the original. For instance, there is a particular thing that appears on the video, and then suddenly this is not processed, and it can appear here. So when you get the slides, you can zoom into this particular image, and you see that there is a very weird appearance of something on the forehead. Okay? So the idea here is that although we have some very good methods, there are still some corner cases which is not completely solved. And then in the second generation, some of them were solved, but still some of the other problems remain. For instance, if you have the conditions that change drastically. So when I say drastically, if the image is captured in the daylight, and if you're trying to create a fake in the nightlight condition, then it will not work very well, right? Because the lighting is extremely changed. And then how much is the distance from the camera? Am I able to create a deepfake of a person who's like 5 meters away from the camera or only 2 meters away from? So this also plays a role, right? And then if you have extreme poses, for instance, the persons on the right side here, so you see that these are, first of all, the quality is low and the pose is very non-standard. The camera is being placed in the bottom side, in the ground, and then the image is being captured. Okay? So this is still some of the open challenges that you can look at that needs to be solved. But despite of these limitations, what we can see is that why are we talking today about this deep fakes? Why should we actually care about this? Now, if I have any face recognition system, I think you will recall this kind of graph from yesterday that we did. We had the ROC and DET. In the case of DET, we want the line to be as close to zero, but in the case of this ROC, we want the line to be as close to one. Just the inversion, right? Okay, so if I have a set of face images that I'm taking with me, and then I'm just trying to run it through a face recognition system, I expect that they're going to be approximately in this area, right? So if the system is very good, so the red line is something that I expect. Now, what happens with the all the kind of different fake images that are produced? And if I'm running it through the system, so you can see all of them are more or less in this region, right? So there is, if I'm just doing face swapping, so the face swapping is here, generic, and then estimated 3D and segmentation plus estimated 3D and segmentation. So all these graphs here, the first three of them, you see the performances. Sorry, the last three of them, you see the performances somewhere here. Make sense? And then if I'm making it even better, so I see that the performance is going all the way up here. So what is this telling? This is telling me that if I have a deep fake images with no prior information, I can attack any face recognition system, right? Which is what we will see later today when we are trying to do the solve the exercise. But does it give an idea that any face recognition system can be attacked using such kind of approaches of creation of fake? Okay? So here is an example of face swapping, but it can also be generalized for other kind of deepfakes, neural textures, face to face, and other kind of approaches that are available. So now this forms the basis for us to start looking into the detection approaches, which we will do on Monday. But for today, did I convince you that there are approaches for creating the deepfakes, and then there are a threat for the biometrics, threat for any kind of security system, right? And the whole of this generation of deepfakes is based on this generative modeling. Okay? All right. Just before I we start with the exercise, let's just take a look at what kind of data sets are available. So there are a number of popular data sets available. This was a snapshot that was taken in a couple of months ago. So we have this TIMIT, which is a data set which is based on this deepfake, and then FFW CelebDF is nothing but the celebrity face image data set, and using that, the deepfake has been created. And then you have DFDC, which is deepfake digital competition. I think deepfake detection competition, sorry, detection competition. And then you have face forensics plus plus, the improvement of face forensics, and then deeper forensics, and then DFDC. So in addition to that, you also have a data set which is, I think, recently released by some of the universities in India, which is on deepfake for the Indian celebrities. And there is also another data set from Korea where they have recruited people, and these are people of these are professional models who could enact in front of the camera, and the video and the audio has been captured. So there are a number of data sets, so you do not have to go back and create these kind of new images, right? Okay, so where are we standing today? So this is a snapshot that I took yesterday night just to see what was happening since 2019. The fonts are extremely small, but I just wanted to illustrate where are we standing right now. So everything that we discussed is up until here, right? We were talking about all these approaches, FSGAN version 2, then you have this blend face swap, and so on. All these are GAN-based approaches. These were up until 2024. From last year alone, there has been a number of new approaches which are based on diffusion, right? So if you go to this link, this is an open publication which is put on archive. On the archive website, they also give a very nice code base. They collect all the code for each of these paper and they put it out there. Not everything is available, but most of them are available. So you can try it and train it, not train it, but try it at least for generation of deep fakes for yourself. Okay, good. So that brings us to the next part. Now we will go to this online demo, and then we can go to the into the code itself. So if I go to this face engine, I think it was this one. So if you go to this one, this particular link, so it's faceengine.ai, and in the faceengine.ai, so the deep face that I showed you in the previous case, the GitHub link, where the code is available, that is the base that is running here. And of course, it's released as a commercial product, but the code base is from that GitHub link that I showed you, right? So here you can go and you can start creating your own links. Let me just change this. So if you go to this face swap, so here you can see how all this are working, and the code for this is available on the GitHub link that I've shared. So it's a bit heavy model, so you'll not be able to run on your local laptops. If you get access to GPUs, then you can just download it and then run it for yourself. Okay, this is one, and then there is also the other one, which is based on another code base that is available. So here you can see that you have this platform called as Generation Platform, and in this case, you are also able to not just create the deepfakes, but also able to put in the prompts. I think where was the prompt one? Here. Okay, so here, right? So now you can see that these models are capable of inserting the text that you want, and then they can generate the video for you, right? So this is exactly the same thing that you will get if you run the code on the GitHub that I've shared. But again, as I told you, we will not be able to run all of those because they are very intensive process to run. Okay, so these are one of the other application, and then there is also this. All these links are available in the slide. So when you get access to slides, you can just click on the links. And then there is also this other one, which is diffusion based approach. As you can see, in the diffusion based approach, you have this paper, GitHub, and Trior model. And if you click on this Trior model, you will be able to run it online. Be mindful again of the fact that the data that you are uploading is stored on their data, on their web server. So there is no way that you can retract. Like if you are very careful, if you want to be sure that it's not used for some other purpose, do not upload your own videos, right? So just have that in the back of your mind. Okay. So now, since we are not able to run all of this, now let's go back to our. Okay, where did that go? Okay, so all the links that we are going to use will be available on the slides that I'm going to give. So let's go back to the place where we have the code now. So were you all able to get the access to the code that I've shared on the day number 3? So you have, okay. So here you have three things that we need to do. Again, just as a tip, I know most of you might be using different kind of Python, different kind of version. So I prefer to use Conda or virtual environment so that you can contain everything to one particular set of libraries. So I have added this instruction. So if you just follow the instruction, the first instruction here, it will Conda create n-phase demo. It will create an environment with Python version 3.10. And then after that, you can activate the Conda environment. And once the Conda environment is activated, this could be anything, right? You could give it as any name that you want. I just named it as face swap demo. And then I've added activation part. And once this is done, so what you can do, you should you should be able to run this command, which says Honda install Forge with the inside face. So what we are doing is that we are taking care of making use of face recognition system, which is called inside face, which is very similar to what we did with the first day one, right? We used elastic face. In this case, we are using inside face, which can also detect landmarks and which can also try to help you to segment the area. And then ONNX runtime to make sure that the model is compact, it's runnable on a local machine. You can also use more sophisticated methods, more heavy methods, but I've just taken that model. And then you need some other operations, right? You need the OpenCV for image manipulation, and then you have the NumPy for array manipulations and so on. Uh, Once you're done, what is also important is you download this model called InSwapper, which is a pre-trained model. So if you try to train the model today, it will not be completed. So I've just made use of the pre-trained model, and the pre-trained model takes an image of takes two images and then does the manipulation and then gives you the output. And the link to download that particular model is given there. If you do not want to go down and go there and download it, you can also download it from the Google Drive that we have shared. On the day 3, there is a small folder called as Insights. You have to just download as it is, and then the code for swapping is provided in the image in the Python file here. And there we are. All we are doing is we are giving two images, and I'm actually putting the model where it should be from. So this is the local place where I have placed the model. and then I'm running it with any two given images, and then I get output image. Okay. Some tips, because you're going to run it on your local machines, so do not try to overload it with 5 megapixel image or 25 megapixel image. That will take infinitely long time. So try to downscale it for, I don't know, 640 by 480 or 480 by 360, something that machine can handle, and then just run it, and then you should be able to get the image. Okay, so now if you're all ready for running this, we can take a small demo. So just let me know when you're ready. No, no, this is that's exactly the reason why I've made it as a CPU version. So for this one, you do not need any GPUs. You can use your local machines. Yes, yes, it will download it from there because it's a third-party version. That happens only one time. So once it is done, you do not need to reinstall them again. So if you follow that Conda instructions, right, the one that I was showing before, yeah. So that will be giving out everything that you need. So you will be set for running the model, and then all you need to do is that insert the put the images together and then just run. And of course, if you are able to get access to get hold of high quality or high computational GPUs, you can retrain the whole model for your own application. In my experience, you would need at least like 24 GB. So you can deal with 20, 12 GB, but 24 is at least needed. So it is, and it will take a couple of days. So we will not be able to run it even if we start it today. But what you can do is that the code that we are going to present, right? So you can run it over the weekend. So if you let it run for today, maybe by Monday morning you should be able to see some outputs. And if you try to use Collab, maybe it will work, but I also know that Collab crashes after 24 hours, and then you have to restart it again. So which there is no point in restarting it over and again. Yeah, maybe premium account, then it would work. Yeah. Yeah. That is the infilling part, right? So you have, in that case, you would have to learn a model where you have the skeleton and the face image, and then you try to learn the mapping. And once you learn the mapping, then you know, okay, if a skull looks at a particular in a particular fashion, then you can refill that one. So what you need to do is that you have the skull images, right? And you have the face images. So you have to establish the mapping between these two. So if a skull is looking like this and the face looks like this, so I learn this mapping. And to learn this mapping, I introduce, I don't know, thousands of skull images, thousands of face images. And once it's able to recreate this to A to B, then I take the model and then I give it a new skull, then it will be able to recreate the face image. So they also do it for sketch to face composition, right? So you have a face sketch, typically in a missing person scenario. If there is a person missing and you only have the rough description of that person, you have the sketch, and from the sketch you will be able to generate the face image, right? So which is exactly the same thing. Only the idea here is that instead of sketch, you are giving the skull image. Right? So there are some other problems, right? The skull can be not in the frontal pose. It could be in side angle. So you have to account for all these things. So it's a matter of training it over and again. Training. Yes. So you need to learn a good mapping between input A, point A and point B. As long as you learn that one very well, so then you're fine. Okay, everybody were able to at least install them. Yeah, good. So now if you have installed it, so let's go to this this part, right? So here I would like to just take few minutes to explain few things. So what did we discuss in the face swap? We said that for any face swap system to work, we need to first detect the face, right? Detect the face, and then we need to identify, right? So either we could do it manually by ourselves, or we could say that instead of doing that, I would just put it as use the existing network, and the existing network in this case is inside face, which has the capability of extracting the landmarks and the face area. Okay. So what I'm doing here in the first part is that I'm just calling that function by saying load the face detector, and then inside that I'm using a model which is called as Buffalo large model underscore L. And remember here again, I'm calling it as CPU execution provider because I do not, maybe I don't have a GPU. If you have a GPU, you can change it to the GPU part. And then again, this is the detection size where I'm saying, okay, what should be my maximum detection size? So I'm telling that it cannot be exceeding more than 640, 640. And after that, I need to put the model where this face swapping is actually happening. For this, what I've done in my case is that I have just placed the a local folder here. In the local folder, you can see that there is inside face. You see that? Inside the inside face, I have this uh, arc face, there is Buffalo L, which we are using there, and then we have the gender age, and then the retina. So all I'm doing now is that I'm going to call this method, and this is the train model, right? So 128 ONNX, and that's the model that I'm calling. So in case you don't want to use the local model, what you can do is that you can also simply call this one swapper get model. And if you do this, so what it's going to do is that it's going to search online and then try to download the model. And then I tried to do run both the configuration yesterday, and for some reasons the networks can break, and then you will not be able to download. So I just download it locally, and then I put it in the folder there. So once I have this, so what I can do is that I'm reading the image, target source image, and then I'm reading the target image, and then I'm saying, okay, from these one, okay, these are the next part is nothing but just to get the source image. In case if I'm giving a frame with multiple frames, so multiple face images, I want to take the most, the first image, right? So if I give an image of the whole of this class, I'll detect number of faces. I only take one face. I'm not going to take all the faces. But you can also have this extend the same code for multiple face swapping. Okay, and then what I'm doing is I'm just calling the function called swapper.get, and then I'm sending the target image, target face, and the source face, and then I'm also saying, should I paste it back or should I create a new uh, image, right? So when I say paste it back, it will put it back into the original frame. And then just to make sure that the content will not be misused, I am putting this text which puts a watermark on that. It just says that it's a synthetic image. I could just also say it as synthetic instead of that. Okay, this is here, and now I should be able to get the output. So let's just run this. So you can run it from here as well, right? So you can either run it from the top part here, run Python file. Then if I just show you the code here, just Okay, you can run it from the terminal here, or you could also do the same thing in this case. Um, so if I run this Python face swap demo, now you can see that it takes a couple of seconds, and then I have an output image. You see the output here now. You could also do it from the terminal inside the Visual Studio Code itself. Okay, so now if I see, I should be able to see the image that I generated now. You see this? So I just added the new synthetic watermark, which is IEEE GAN Lab, and that comes out there. And from the image that I generated yesterday night, let's just see what happens here. So yesterday night, the image that I generated is here, and then if I take the images which was used for creation of these images, faces, source. I think this was the first image. Okay, you see them now, right? So the bottom two are my source images. So I've taken two different people, and then I've created the image there. And you can clearly see that this person has the lips of this person. See that? And then this person has the appearance of this one. So I'm transferring these two into this, and the other time these two into this one. Okay, so now anybody can tell me about some limitations in just by looking at these images. And if you look at them, right, the quality is also quite high. You see that there is no visible artifacts that we were discussing in the first part of the lecture. Any any obvious thing that something comes to your mind? The spectacles. So that is one, yeah. The lips are not very well aligned. Good. The ears, yes, the ear is also not extremely well aligned. The reflectance is also not great. Yeah. So what about the now you have already started identifying these artifacts, right? These are the artifacts that we will use to learn the detection modules later on Monday. But now, what about the ethnicity? Do you think it's good to merge Caucasian with the Chinese? Let's assume that if I'm to give this police officer, and I say that this is me with two different ethnicity, can I merge my face image with somebody from, let's say, from US? All right. So then, whenever you are creating this fake data, or whenever you are creating this deep fake data, there are also certain considerations that you need to make. Some considerations like the sample should be of same age group, right? You cannot be a 4-year-old with a 20-year-old, right? So it's two different age, and the gender should be similar or same, and the ethnicity should be same, right? So only then you get high quality data. Okay, so now if you have all generated this one, let's see if it really has an implication on the security. Let's go back to the first exercise that we did on the face recognition, and then try to match the generated image with this image and see what is the score we get. And then also try to do the same with this one and this one, this one and this one, this one and this one. So we'll try to do comparisons. Okay, so for that, the code was called as Lab 1 Practical, right? So where was the picture one? So this was the code that we started, right? So we started with a simple model which we where we introduced elastic cost phase, and then we ran this comparison just to see what was the score that we were getting. So what we will do is now we will take the same code, and then we'll try to see what happens when I have generated the deepfake images. Is the score going to be very high, or if the score is going to be very low? Okay. So I am going to just put the block here and then copy the path. So I'll just name them as original one, right? Original, original one, then original two, and then here I call them as swapped output one. Okay, so all I'm doing is that I'm reading the four images that are two original images and two manipulated images, and then I'm going to dump the features. So to do this, I just need to run some of these blocks again. This is done. This is done. And then this is done. Again, I'm loading the same image, right? It's the same model that we used on day one. And then here I'm going to create four different template files. So I have four different template files. Now I can just do a comparison. So what was the comparison? Original, original one versus original two. Similarity score. original pairs. And then I'm going to do the same with the next one, original one with manipulated one. Okay, and then it is manipulated pairs, and then it is 1 versus 1, 2. Then manipulated, oh, sorry, original 1 versus manipulated 1, and then original 2 versus manipulated 2, and then the pair is 2 versus 1. Okay, so let's see how the cosine distance varies. Now you see that the original pairs had a score of 0.41, right? Sorry, the original pairs, which is the lady on the picture and the man on the picture, they got a score of 0.31, which is understandable, which means they are not the same people. Now, as soon as I swap them, you see that the score actually increases quite a bit. It goes to 0.41, and in the second one, it goes to 0.51. So, which means the system that was rejecting the two people in the first place is now starting has now started accepting the people as genuine users, right? Or the same pairs. Okay. So what you can do for is everybody able to run this code? I'll also upload this code, the face recognition part, but then you can just loop it through multiple images for all the images that you have generated, and then try to see what happens with the DET curves. Questions?
Hello, Kiran. I am audible.
Yes, Praveen. Now you are audible.
Yes, the question is there because this all stylian and then all model is training on very high resolution images. Suppose we are testing on the low resolution image and then the same type of effect is there or some other artifacts or some different type of morph face is generated.
Okay. The question is here we are generating the thank you, Praveen. Here we are generating the high quality images, right? So in this case, we clearly see an impact that okay, the score is increasing. So what happens if you have low quality images, right? So as it again depends on the face recognition system that we are using. If the model is trained to deal with low quality images, then score would be still same. Maybe it will not go from 0.301 301. Maybe it will not go from 0.30 to zero point 0.4. It will be slightly lower. Okay, let's test it out. What is stopping us from testing it out? Let's go here, and I take the swapped image, and this image I'm going to reduce the size. I'm going to make it extremely small. I think I can just blur it out just to see what happens. Okay, so I'm going to degrade the image. Sufficiently low quality image.
Yes,
Okay,
yes.
let's just save this. And let's just copy the output from the previous case. So this was the output that we got. I'll put it on a simple. So I'll copy the cell output. Okay, so this is from the high quality. now let's do the same thing for the low quality. Going to run this. So the face recognition system did not complain. It extracted the features for all the four images. Okay. Now let's see what is the impact of that on the comparison score. Now you see that the score on the last one decreased.
Yes.
You see this? So in the previous case, it was 0.51.
Mhm.
So in this case, the score has decreased down to 0.31494. Okay. So you can still have a quality, but what is interesting is also to note this one, right? In the original pair, it is 0.30, while in the second one, although the quality is lower, it is still higher. The comparison score is going higher. So which means that even with low quality images, not 100%, at least you'll have a success of more than 60, 70. Okay? Thank you, Praveen. I think it was a nice demo.
Thank you, Kiran.
Okay, let's try to do one more thing. Since we have 10 more minutes, I can try to see if we can do something with the gender. Check. I just had to change it from TensorFlow to something else. So this some of this code might be completely not readable here. One. Okay, the gender module is not working, but I'll upload it so you can just train it again. Sorry, test it out again just to manipulate that. So you can just manipulate age, gender, and other things. Everything that's available in this part in the model here. Everything that was available in the inside face. Inside face. Go here. So you can see that there is gender and age manipulation, and then there is race manipulation, and so on. You can try it out. Um, for those of you who want to get started on diffusion-based deepfake detection, I will also upload this code, which is Deepface. This one. This is a bit of a heavy model. Uh, you can you can run it on your system if you have a good GPU. All right. Okay. So that is what I planned for today. If there is any question, everybody were able to run the code. Those who tried halfway, you're getting an error. Uh, it is the yeah, yeah, yeah. Yes, that's right. That's right. Yeah, that's right. Yeah. No, no, no. It will not start raining. It can. You need to open it. So yeah, that is loading the model. Yeah. So if you're training it, then you should not use that command. Okay. Anybody else who has some issues? It's a decoding plan. So you did not run it yet. Okay, we can run it. All right. So if questions, I don't know how long we are having. We are yes. Okay. Uh, Interesting question there. So what can we do with the existing code? Some things that you can do is that this code that I've given you is the inside face, which is already pre-trained model, right? But if you go back to this, let's say for this, I will also upload this deep face. Deep face is another technique which is based on GAN approach, and there you can go into the code, and then you can try to change the architectures. For instance, here, this, not this. Yeah, for instance here, right? If you try to do it from the scratch itself, so here you have all the notebooks that are available where you can go and try to play with attributes and also the aspects like age and gender. There is another place which I want to show you. Let's see. Okay, here, uh, as you can see on this part of the code, right? So you have a number of places where you can play with. For instance, you have what kind of process that you want to use in the diffusion, what kind of losses do you want to play with. So typical losses that are KL divergence and others are there. Maybe some of them are better for some use cases. This is something that you can train on your own data sets. And then you could also change the configurations. For instance, here there is a configuration of how the attention is provided. So this is another place where you can play with. But again, all these things, whenever you play, you need to retrain the model and check the consistency of this training. Right. So I don't think I have more things, but these two codes also I will upload it along with the instructions on how to use it for training. Other than that, I think most of you are able to run the code today. At least those of you you're done for today. Okay. So then, in case I wish you a good, nice, happy weekend, then we see you on Monday morning.